Gems, welcome back after a while. This is the question bank series. This is our grind for BITSAT 2025. With every episode of this series, we are getting 10 questions stronger in every BITSAT chapter. Okay, so that is the motto of this series. Okay, I hope you are following. If not, we have covered up the 11 standard chapters, all the 11 standard chapters. So if you want to have a look at it, the link will be available in the description box of this video. Okay? Also, we have finished some 12 standard chapters, and before session 1 we shall finish all of this. Okay, so you'll have a total resource of most relevant questions. Okay, at least the questions on most relevant topic for BITSAT, so you can use this series and practice more such questions based on those specific topics and boost your score for BITSAT 2025. This is how you should approach this series. Okay, so today we are discussing the chapter of electromagnetic waves. So we won't go into the trends of this. Basically, the topics that are important is firstly you'll have Maxwell equations, so that topic is important, and then we'll have the different electromagnetic waves, okay, gamma, X, UV, IMR, and their wavelength and their frequency. The at least the trend you should know. So we'll practice questions on those and their application. Okay, so those three topics are important, and we shall directly hop into the lecture today. So question 1 and 2 over here for today. So question 1, we have a figure, we have a capacitor, okay, parallel plate capacitor is charged by this battery. We are shown two curves X and Y, closed curves in it. You are supposed to tell this integral BDL. Now you know this BDL is nothing but, if you know the Ampere circuital law, it is this, right? BDL is mu naught times I enclosed, okay? Using this you can in fact find uh, the magnetic field due to loop and straight wire and so on. Okay, so this makes it simple, right? But here there is a catch, because if you haven't learned this chapter earlier, this is not the correct form. Okay, at least as per this case, it is not correct. Okay, we'll have one additional term which is, okay, mu naught times ID. Okay, so this current is the enclosed current plus this displacement current. Okay, so this is a new concept which you are introduced to in this particular chapter. If you don't know about it, I'll tell you in brief what it is. Okay, so of course the conventional current you know. So across loop Y, you have this I enclosed, right? This current which is flowing when the capacitor is being charged. There is some current flowing, right? So this is I. So this is during the charging process. Okay, so the current I is flowing. Okay, and what about between the plates of the capacitor? Now you'll know, in between the plates of the capacitor basically blocks DC current, right? So it won't allow as such a current, conventional current, to pass through, okay, pass between the plates of the capacitor. Okay, so there is current over here. In fact, there is current over here, but what happens to current in between? Okay, and in fact, a revolutionary idea was built up, and you'll see in this chapter that there is current between the plates of this capacitor, and it is not just the conventional current. Okay, it's not actual flow of charge, it's this displacement current. Okay, this displacement current, so which won't be zero. Of course, here there is no enclosed current, but there will be displacement current. So in both the cases, you'll see that um, in the case of Y loop, okay, there is this current I, okay, I enclosed we can call it, and here also there is some current ID. Okay, if you want to read more about it, uh, check your NCRT. So basically, it's defined as this epsilon naught d phi by dt. Okay, so electric flux is changing, right? So as the charge is getting accumulated on the plate, electric flux between the plates is changing. So due to that, we have this current. Okay, and that explains this, where this current is going in between the plates of the capacitor. Okay, one of my most underrated video, just 20 to 30 views on that. Anyways, so yeah, so we have current here in this loop X, and in X and also in Y. Okay, so since there is current, there will be magnetic field. Okay, so here neither D or X, neither X or Y. Okay, so because this will not be equal to zero, because both of these are present, right? In this case, when you are outside and you are considering the Y loop, this enclosed current is there, okay, which is flowing due to the battery. Inside, when you come between the plates of the capacitor, there is this enclosed current is zero. So you might, if you just knew this law, you might think that for plate for this X loop, it should be zero. So you might mark this option, but actually the modified form of Ampere circuital law is this. Okay, so it also accounts for the current between the plates of the capacitor. In fact, if you place a compass between the plates of the capacitor, you'll see a deflection. So there is magnetic field, which means there should be a current. Okay, so which is the displacement current. So that is briefly a sense of it, and both these currents are equal. Okay, that is some extra knowledge. So I enclosed or the conventional current. Okay, so whatever current this is, that is equal to the current which is flowing inside. Okay, there is a proof for this in your NCR. So let's come to this question. Here we are given out of the following, which one will produce a propagating electromagnetic wave. Okay, so if you see a stationary charge will produce electric field, right? But it won't have a tendency to produce magnetic field, right? Moving charges produces magnetic field. Current is what? Flow of charge, right? Flow of charge produces magnetic field. Okay, so a stationary charge will produce electric field, but not a magnetic field, and hence no electromagnetic wave. Okay, so that's wrong. A chargeless particle will not produce electric field in the very first place, right? So it will not be able to produce this E of electromagnetic wave. So yeah, that is also not the correct choice. Let's come to accelerating charge. Now some of you might know it as a fact that accelerating charge produce electromagnetic wave. Okay, this is a fact today, but a century back it was not. Okay, it had to be discovered and by brilliant minds, of course, and accelerating charge do indeed produce electric field. Right? So if you see if a charge is accelerating, first of all, a charge is there, so it will produce electric field. And since it is accelerating, it is moving, so we have flow of charge, right? Flow of charge, electric current, so it will produce magnetic field. And both of these are spatially changing, right? Since the charge is being accelerated, they are changing with space. Okay, the electric field and the magnetic field. Since the charge is moving with acceleration, they are changing with space. Okay, and that space varying electric and magnetic field will produce, so space varying electric field will produce time varying magnetic field and vice versa. Okay, so we have a propagating electromagnetic wave. So that is the correct choice. So if you see a moving charge at constant velocity will not produce electric field. Of course, it produces electric field, also magnetic field, moving charge, right? And it's a charge, so electric field is there, magnetic field is there since it's moving, flow of charge, but it won't be spatially varying. So for that, you need an accelerating charge. Okay, so it will produce electric field, magnetic field, but not your propagating. It will not make it propagate. Okay, so accelerating charge produces electromagnetic wave. So that's the idea behind it. Over to the next set of questions. Discuss question 3 and 4 over here. In question 3, we are given the electric field and the magnetic field associated with, okay, we are asked for electric field and magnetic field associated with a wave which is propagating along the positive z axis. Okay, so if you see the formula for this is, can use C cap is equal to, this is for direction only, please don't use it for magnitude. Okay, so that's why I'm using unit vectors. Don't use this formula for magnitude. Okay, so the propagation will be E cross B. Okay, so E cross B should give you the direction of the magnetic field. Okay, so you can use your right hand thumb rule. Okay, so what direction do we want? We want the propagation along z axis. So this should be k cap, right? Or z cap, whatever notation you use. So k cap is along the z axis. Okay, so this should be along the positive z axis. So plus k cap. Okay, if it was negative, so minus k cap. Okay, so we'll see what cross product will give us this k cap. If you see k cap cross I cap, if you know this I cap, j cap, k cap, right? So this is how you remember the cross product thing. So if you go in the cyclic order like this, so one or two multiplications will give you the next one. For example, so k cross I. So k cross I will give you j cap. But do you want j cap? No. So this and this, if you multiply, you'll give it will give you k cap cross I cap, j cap. But we want k cap, right? We want positive k cap. Okay, so this is not the correct choice. Let's come to this one, j cap cross j cap. Of course, a vector with a cross product with itself is 0, right? Because the angle between them is 0 and sine 0 is 0. AB cross A cross B is AB sine theta, right? Sine theta is 0. That cross product will be 0. Okay, so this will give you 0. Okay, and in fact, it cannot be EM wave because you should have like perpendicular electromagnetic the electric component and the magnetic component should be perpendicular to each other, right, in an EM wave. Okay, and also that will be perpendicular to the direction of propagation. So all these three will make the three axes I, J, K. Okay, that is a hint. Okay, so all three should be different. Basically, I'm saying. So see if you come to this J cap and K cap. J cap cross K cap. Yes, this is no. J cap cross K cap will give you I cap, right? J cap cross K cap gives you I cap. Okay, remember that the order matters over here. And finally, if you see now, this should be correct. I cap cross J cap, K cap, right? So if you see, so this should be I cap cross J cap and E naught and B naught, right? So if you want, but we don't use this for formula. Uh, this formula for the magnitude. So I cap cross J cap will give you K cap, right? And we want that direction. So yeah, electric field will be along the x-axis, magnetic field along y-axis, and hence we'll have propagation along the z-axis. So remember this formula and use it only to determine the direction. Let's come to this one. Here we are given the magnetic field of a wave. We are supposed to tell its wavelength. Now, for this, you are just supposed to know the equation of wave. Okay, even if you know it from 11th standard chapter, it's fine, right? So here it will be something like B is equal to B naught, uh, sine or cos. So sine is there. So we'll compare it with this form kx plus or minus omega t. Right? So here we have plus omega t. Okay, so kx plus omega t. This is the equation of wave, right? EM wave is also a wave. So if you compare this, we want wavelength, right? K is what? K is 2 pi by lambda, right? So from this we can get the wavelength, right? So we'll compare the coefficients of x. So here it is says 10 to the power 3 pi, right? And what is the coefficient of x over here? K. Okay, so from here we can find the uh, wavelength. So this is 2 pi by lambda, right? Pi cancels, and this is 1000. 1000 by 2 is 500. So lambda is actually we'll take this over there. So 2 by 1000. So 1 by, or will not change it. So 2 by 1000 or 2 into 10 to the power minus 3, right? Because we want the answer in that form. Okay, so where is that? Option B. Okay, so it's like 2 millimeters, right? All the options are in meters. Okay, so everything is in standard unit. This x also will be in meters. Okay, so we just compared the coefficients of x, this with the general wave equation. Okay, so that's the simple concept behind this. Over to the next question. 5 and 6 over here. Question 5, you are asked for the energy density of EM wave in vacuum. Now, what is energy density? It is basically your energy per unit volume. Right? So, this is asked for the EM wave. Now, there is a standard formula. I won't go into the details of this. So, first of all, you can see that option C will be incorrect, right? Because it is field. Okay, you are asked for energy density, energy per unit volume. Okay, so this answer is purely in terms of field. Okay, now this question realize whether you know the correct relation. Okay, and if you see, to remember this, actually you can do is that they will have opposite sense. Okay, so B and mu, epsilon naught and mu naught will appear in opposite. Okay, so like one will appear in the numerator and the other one will appear in the denominator. So remember that. So what two options are there? So this one also becomes incorrect. Okay, so that is how it is balanced dimensionally, right? So I'm giving you the logic behind dimensional analysis of it. So here also if you see both are below, right? So this should be the correct choice. Okay, and the formula itself says this is the electric part. Okay, so this is the electric part, half epsilon naught E square. Okay, actually it's epsilon E into D. Okay, so D is what? Epsilon naught E, right, for vacuum. So it becomes epsilon naught E square, right? And the magnetic part is B square upon 2 mu naught. So half factor is there in both. E square, B square is there. Okay, but this also will be okay, and this is times, right? Because this is E into D. So that also you can remember. So this is E into D. So this will become, so epsilon will come in the numerator. So mu naught has to come in the denominator. Okay, so that is the idea to remember this. But yeah, some of you might directly know it. Good for you. This is a important formula because so this is the electric part of the, this is the energy stored in the per unit volume for the in the electric field, and that is the energy stored per unit volume in the magnetic field. Okay, so yeah, you can individually remember the formulae. They can also ask you for that. Okay, so yeah, let's come to this question. This will test your concept on what happens when a light travels from one medium to another, specifically an electromagnetic wave more generally. Okay, so we have frequency of 3 megahertz. It passes from vacuum to some dielectric medium. So it passes from vacuum to some dielectric. Okay, so it will slow down, right? So this has relative permeability of 4.0. Okay, so what is this relative permeability? So mu r, right? Permeability. Permittivity will have in epsilon naught, epsilon r, right? So this will be this is relative, right? Relative meaning ratio. Okay, one with respect to other. Relative. You are comparing. Okay, so this will be the actual. Um, Actually, this is by mu naught, right? You are comparing it with mu naught. Okay, and the relativity of the medium. Okay, so this we can call medium 1. Okay, so mu 1 divided by mu naught. Okay, so this is what relative permeability is. Now you'll know that speed of light. So basically we are asked what happens to the final wavelength as compared to the initial wavelength, and what happens to final frequency as compared to initial frequency. Now one key point is that frequency depends on your source, right? It does not depend on the medium. Okay, so the source which is emitting this electromagnetic wave, that will determine its frequency. Okay, although it travels to some other medium, that won't change its frequency. And the frequency will remain same. Okay, so which one is that option? So option C, B or D. Sorry, B or C, or even D maybe. Okay, so frequency will not change. That is something to remember, and we can also see it by the relation C is equal to F lambda, right? So we know that speed changes, right? That's why the light is bending. Okay, light slows down in a optically denser medium. Yes, we'll revisit that in our next chapter, ray optics. But yeah, so C is equal to F lambda. So C is changing, right? Um, so what has to change? F is not changing. We have established that, but lambda has to change, right? So C is changing, then lambda also has to change. Okay. So now by how much? Okay, is it half? Now this option will also go because lambda can't remain same and F cannot change. Okay, so these two options you can neglect. So either this or maybe nothing of them. Okay, so how will you determine this? Now C has a simple formula. It is if you want speed in any medium. Okay, so V we can write V because it is in some medium, right? So I can also write V over here. Okay, so V in any medium will be this mu epsilon. Okay, or in vacuum it is mu naught epsilon naught. Okay, 1 by root mu naught epsilon naught. Okay, so what is happening? So we can write this as what is mu? Mu is of that medium, right? Mu 1 epsilon 1. This is for the medium. This is for vacuum. Vacuum has mu naught epsilon naught, right? Because this mu r basically is 1. Okay, so these two quantities become equal. Okay, so vacuum is basically this, and the more general case in any medium. So it is mu 1 of that medium, epsilon 1 of that medium, right? So how is mu 1 given? Mu naught times uh, mu r, right? And mu r we are given it is 4, and here also epsilon naught r, epsilon r. Okay, so same. Okay, so epsilon r because it will be also relative, right? Epsilon naught divided by epsilon r, relative permittivity. Okay, so now what will be V? V will be, so we can separate this out, mu naught epsilon naught and mu r epsilon r. Okay, nothing is given about epsilon r. Okay, we'll consider it as 1. Relative permittivity is given. So we'll consider epsilon r as 1 in this case. Although it's not mentioned in the question, that is how we'll be able to solve this question. So you can take a guess from the options also now. Because if you see, yeah, epsilon r when it becomes 1, this and this will remain, and under root of mu naught r. So mu naught r is 4. This is basically K, right? Relative permeability, which is mu r, relative permeability. So mu r, so this is basically 4, square root of 4 is 2, so 1 by 2, right? So the square root of 4 is 2. And what is this? The C, original speed. Okay, so what is happening when the light is traveling from vacuum to this medium? The speed is becoming half. Okay, so speed goes from C to C by 2. Okay, So basically we found out the speed in the second medium. That was the objective I was behind. So we used this formula and we found out the speed. So speed goes from c over here to c by 2 in this medium. Okay. So frequency remains same. So what should happen to the wavelength? Right? What should happen to the wavelength? It should also become half. Right? C has to become c by 2. Lambda has to become lambda by 2 because c is equal to f lambda. Right? I kept it that way. Okay. So c is equal to f lambda. So c is proportional to lambda, right? Because f is constant over here. Frequency is not changing. I told you it depends on the source only. So c becomes half. So lambda will also become half. Okay. So that this option is correct. So your final lambda will be half of the initial lambda, and that's why you can say the speed is decreasing. Okay, and there is no effect on frequency. It depends on source only. So that was the key concept behind it. Over to the final two questions for the day. 7 and 8 over here. In question 7, we are given certain statements. We are supposed to tell which one is correct. So frequency in increasing order is. Now I remember it this way: gamma x u v I m r. Okay, so this is the direction of increasing wavelength. Okay, so wavelength and frequency, are inversely proportional. C is constant, right? For a given medium, C is constant. So speed of light. Okay, so speed of electromagnetic wave. So lambda is increasing, so frequency will decrease, right? Because lambda and frequency are inversely proportional. Okay. So in the previous case, we had frequency same because it was traveling through two different mediums. Here we are speaking of one medium. Okay. One medium, C same. These two are inversely proportional. Okay. So if wavelength is increasing, frequency will decrease. Okay. So you can remember it this way: gamma XUV IMR, grand XUV in my resort, whatever. Okay. So this is how lambda increases. So this is how frequency will decrease, right? So lambda increase or frequency decrease, because this is same, right? Because they are inversely related. So this is lambda increase or frequency decrease. Gamma XUV IMR, lambda increase. Okay, you can remember any one. So the other one will be opposite, right? So if lambda is increasing, frequency will decrease. Okay. So what are they saying? Frequency in increasing order is. So how is the frequency increasing? Okay, so this is how frequency is decreasing. How will be the frequency increasing? This way, right? So this way frequency will increase, wavelength will decrease. Okay, you need to memorize this entirely. Just remember grand XUV in my resort, gamma XUV IMR. Okay, and in that direction, gamma XUV IMR, in that direction, lambda increases. Okay, lambda increases, frequency decreases. If you want the other way around also, so here in this direction, lambda increase, frequency decrease. In the other direction, lambda will decrease, frequency will increase. Okay, so it's easy to remember. So just remember this part. Okay, gamma XUV IMR, and lambda increases in that direction. So frequency will increase in the opposite direction, right? Gamma XUV IMR. Yes. So this is correct, but don't jump to conclusions because we have all of the above. Okay, so anything can be correct or everything can be correct. Okay, so wavelength in decreasing order of this. Okay, and also you can remember now, if you have remembered this with your, right, the colors in your rainbow: violet, indigo, blue, green, yellow, orange, red. I hope. Okay, so this way the wavelength increases. Same. Okay, so you don't have to. Uh, there is no chance of mess up, right? So gamma XUV IMR with your both in the same direction, lambda increase. Okay, red has the highest wavelength. Okay, that is why you have a red signal. Okay, because they don't get scattered easily. It has a longer wavelength, less chance of scattering easily, right? And so it can be visible, right? It's more visible, and red signs are used almost everywhere to stop you or to make you alert, right? So because red scatters less, it has the highest wavelength. Okay, so you can relate all these things. So this is also okay. This is also correct, but since we have all of the correct, okay, these two are correct statements. Okay, but the correct option over here will be option D. Okay, since two of them are correct, only one can be correct for BITSAT. So that makes this correct. Okay, okay. Uh, Okay, C also we can confirm. Okay, but since these two are correct, option D will be correct, right? Because BITSAT is single correct, right? So, and there is option which says all are correct. Okay, so I'm not just messing around with your head. So option C, speed of light is maximum in vacuum, and this is of course true. Speed of light is maximum in vacuum. In other medium, then there is that mu r factor, epsilon r factor, right? So those are always greater than one, by the way. Okay, so that will lower the speed of your light in some other medium. Okay, so that is also correct. Option D is the correct choice. Okay, so although all are correct, the one that is saying all are correct is correct. Okay, so anyways, I'm so much dwelling on that. So let's come to question 8. Here we are supposed to tell what is correct for X-ray and gamma ray. Okay, again there is this option, so be careful. This might come in your exams too. So don't be tempted to just verify the first answer and just tick it off. Just check when you have the right answer, do check if the option has all of the above. Okay, so that might be a trick played. Okay, you never know. It's a easy way to lose marks, right? When you know the answer. Okay. So let's come to this one. X-ray are electronic transitions, and gamma ray the source is nuclear transitions. And this is true, right? This is true because how can you relate to this? Okay, in X-ray, you might learn about the K alpha, K beta lines, right? So they are from the K shells. And where are these K, L, M shells? In the um, electronic, right? In the your electrons orbit in those shells. So you can remember it if you have learned the K alpha, K beta transitions in X-ray. So from there you can remember this X-ray are electronic transitions, right? They appear when electron transitions from one level to another. Okay, so and that is a major point of difference between your X-ray and gamma ray. Gamma ray are in fact nuclear transitions. They happen. You study gamma what is that called, beta decay, gamma decay, right? So gamma decay, so those are the release wave is a gamma wave, right? And it is a nuclear process, right? So gamma rays arise from nuclear transitions and X-rays from electronic ones, K alpha, K beta, right? And this is gamma decay. You can remember it that way. Then let's verify other options also, or only this will be correct. So X-ray has low penetrating power in comparison to gamma ray. This is also true. How can they relate to this? So if you X-ray, one application is medical application, right? It is used to pass through your body and get the image of where the fracture is, right? So how is it able to do this? Sorry. So because it has low penetrating power, okay, so it cannot pass through your bones. So it passes through the skin, but not through your bones, and it leaves that imprints. Okay, so that is maybe the um, qualitatively the idea behind X-ray. Okay, so yeah, it has low penetrating power as compared to gamma. Gamma will pass through you. Okay, so that way you can remember. So two are correct, which means D is also correct, which means D is correct, which means all the options are correct. You can also verify this. Uh, Frequency of gamma ray is greater than the X-ray. Yes, right? Because this way frequency increases. Okay, this way wavelength increases, this way frequency increases. That way also you can remember. Okay, so yeah, all three are correct, which means option D is correct. All of them are correct. Okay, so uh, that is about today's session. I hope you enjoyed it. Keep following the session. This will help you boost your score for BITSAT 2025. We'll cover up all the chapters, and yeah, that's hopefully it for today's chapter. Do learn the applications of all these electromagnetic waves from your NCRT. Just pick up. There will be one table which will have applications of all these waves. They might, you never know, they might also ask this. So do make a short note of this, or have a small picture of this, so you can revise the applications of this all these electromagnetic waves. Do remember their wavelengths and specific range also, so that might help you in exam. So yeah, that's about today's lecture. I hope you enjoyed it. Go watch the other relevant questions on other chapters, playlist in the description. I'll see you soon in the next video. Till then, keep enjoying physics.